to Sergio's Structural Engineering channel. There is a long time that we don't perform a simple example in the blackboard. Okay, it's time to recover this kind of exercises. Today we are going to study which is the base shear for this simple structure due to seismic forces. Okay, we analyze this structure. We are having a reinforced concrete solid flat of 30 centimeters thickness. Okay, that is supported over 8 columns, which dimensions are 400 per 400. Okay, the complete compressed strength, it is assumed of 25 megapascals. Okay, and these are the loads that are estimated over the flat slab. For permanent loads is dead loads. Okay, in Spanish is permanent. Okay, it's 2 kilopascals. For the live load, for sobrecarga de uso, live load is 1 kilopascals, and we assume that the cell weight of the solid slab is equal to 7.50 kilopascals. The aim of the video for today is to deduct which is the equivalent seismic forces acting against the structure. We have some. This is a particular simplified method to try to make it simple. Dynamic analysis, normally modal analysis. Okay, so it is also this methodology is collected in many design codes. So, for example, in Eurocode 8 it is called lateral force method. Okay, in every kind of dynamic structural analysis, it is essential to determine which are the masses acting over the flat slab, the roof slab of this structure. Here we have all the values represented, okay, and you can see the sum of all the masses take into account the cell weights of the RC slab, the permanent load, the dead load, the live load, or even including the cell weight of the 100% weight of the columns is equal to 164,000. We have to do in order to study any dynamic problem or seismic problem is to achieve the value of the stiffness of the structure. Okay, if we are going to fix our attention in a transverse section, okay, call it AA, and we represent it here in the blackboard. Okay, we are going to have the RC slab, and here a column, and here another column. Okay, for this simplified exercise, we are going to assume that this value of stiffness is infinite, rigid. Okay, and the columns, okay, have whatever the stiffness or whatever the flexural value that they have. Okay, we have to study the stiffness in terms of lateral displacement of this frame. Okay, and we assume that this structure is have only 1 degree of freedom. That's why we are calling single degree of freedom, only lateral movement. So if we imply some kind of force here, the displacement of the structure will be that way, and then a rigid body or the RC slab is going to move that way, and the displacement will be, call it delta. Okay, the stiffness of this kind of a structure, according, for example, like authors like Chopra, it is like for a single column, we say that this equation shall be followed. Okay, assuming of course that the height of the column of the frame is well. This is here deducting the values of the equations that we need to generate the global stiffness provided by the columns. Here we have the second moment of inertia. Okay, that is equal to b square to the fourth divided by 12. Okay, we're going to consider the gross section. Maybe we can think about it to be a crack. Okay, but for this exercise we are going to keep the idea to have the second moment of inertia for a cross section. Okay, the modulus of Young. Okay, the elasticity modulus of the concrete. This is the value provided by Eurocode 2. Okay, and then we have to deduct the global stiffness provided for the 8 columns. So we have like a 97 million newtons per meter as a global stiffness in the lateral direction for the frame. In every single dynamic analysis, it is essential to get the value for the natural period or frequent period of vibration. Okay, for dynamic theory, we know that for a multiple degree of freedom, a structure with several degrees of freedom, we can deduct the frequencies or periods of the structure according to this following equation. Okay, it's a determinant of the stiffness matrix. Okay, minus angular frequency and multiplied by masses matrix. Okay. This is for a general structure. In case we have a single degree of freedom, okay, and equal to 0, it's important because it's like the free condition. He can vibrate in a free condition, okay? If we have a single degree of freedom, like our case, okay, this matrix converts in one single value, okay? So if we try to manipulate this expression, we have the angular frequency is equal to the square root of k divided by masses by m. Okay, we know that angular frequency is equal to 2 times p frequency. Okay, and frequency can be also expressed in terms of period. So if we take this expression and put it in this part, we say that the period of the structure is equal to 2 times p, the square root of stiffness divided by m. Okay. For this case, as we have only 1 degree of freedom, we are going to have only one frequency value or period value. Very simple now. Let's apply the equation for the natural period, the first period of the structure, assuming 1 single degree of freedom, and we get the value of 0.258. We have deducted the dynamic parameters for the structure. It's necessary to define like a design linear and elastic design spectrum to define the acceleration for the place and for the soil. Okay, so we have to get to design codes where those spectrum are defined. Okay, this spectrum shows in the x-axis the period of the structure. Okay, the one we have deducted just a few minutes ago, and here in y-axis we have the accelerations in terms, of course, of the period. Okay. This spectrum corresponds to one spectrum placed in Switzerland, in Palermo, okay? Because it was one of my latest projects I was involved, okay? As you can see, here is a typical shape of this spectrum, and if we focus in this area is where we get here, this flat area is where we get the maximum acceleration. That for Palermo is equal to 3.6 meters divided by square seconds. Okay, so the first thing we have to do is take the period of the structure, 0.25. If we show it is placed here between 0.1 and 0.42, and then, as you can see, the acceleration to be applied for our calculation, it is the maximum value defined by this. Let's deduct once again what is the base shear for the structure. Remember that the base shear is going to be the forces applied here, what is assume the single degree of freedom. Okay, so we are going to use equation 4.5 according to the actual version of Eurocode 2. So we have this expression, we have the acceleration already defined minutes ago. We have to multiply acceleration per the summatory of masses here in the first point. And also there is a factor lambda, okay, that is defined in Eurocode 2. We are going to assume for the safety, for a conservative point of view, the value of 1. So the base shear due to the seismic in this location in Switzerland is equal to 600.24 kilonewton.
You know that we would like to also to compare our simplified calculations with the results or the output for commercial softwares. Okay, in this case we are comparing with SAP 2000. Okay, as you can see in the left corner, upper left corner, you will follow you can see the period of the structure in transversal dimension. Okay, 0.28. Okay, very close to the 0.25 that we have deducted. Okay, and you can see the vibration or how the structure vibrate according to this first mode or natural mode. If we would like to design the structure that is represented in the screen, my suggestion is to divide it, the base shear divided by the number of columns. Okay, and apply horizontal forces, in that direction. Okay, in the top part or the top joint of the column, as you can see in the screen. Okay, so if we now perform the analysis, the structural analysis. Okay, and then for example we pay attention to the RC columns and we request to the program the bending moments, you will find these diagrams. Okay, that they are typical. They are typical when you have a great amount of lateral horizontal forces. Okay, the bending moment is only due to the seismic forces, so there is no combination with other single loads.
We reached to the end of the video for today. I hope you are enjoying the content of the video. Please subscribe, comment, or even if you decide, please give a like. And remember also that this is able to access to more information regarding construction and structural engineering through the social network LinkedIn, through my profile that is shown in the screen. I hope to see you soon. Take care.